Welcome to this lesson on radioactivity, one of the most fascinating phenomena in modern physics. Radioactivity is the study of unstable atomic nuclei and how they spontaneously release energy and particles through a process called decay. This natural phenomenon was discovered in the late 1800s and has since revolutionized our understanding of matter, energy, and the atom itself. Throughout this lesson, we will explore what makes certain nuclei unstable, the different types of radiation they emit, and the remarkable applications of radioactivity in medicine, energy production, and scientific research. Radioactivity is defined as the spontaneous emission of particles or energy from unstable atomic nuclei. But what makes a nucleus unstable in the first place? Nuclear instability occurs when there is an imbalance between the number of protons and neutrons in the nucleus. When this balance is disrupted, the nucleus contains excess energy and becomes unstable. To achieve a more stable configuration, the nucleus undergoes a natural process where it transforms by releasing radiation. This transformation is completely spontaneous, meaning it happens naturally without any external influence, and continues until the nucleus reaches a stable state. To understand radioactivity, we need to understand what distinguishes stable nuclei from unstable ones. Stable nuclei have a balanced proton-to-neutron ratio, where the strong nuclear force successfully holds the nucleus together, overcoming the electrostatic repulsion between positively charged protons. In contrast, unstable nuclei have an imbalanced ratio that causes instability. When the forces within the nucleus are not properly balanced, the nucleus has too much energy and must undergo radioactive decay to achieve stability. During this decay process, the unstable nucleus releases energy and particles, transforming into a more stable configuration. There are three main types of radioactive decay, each characterized by the specific type of radiation emitted. First is alpha decay, represented by the Greek letter alpha, which involves the emission of a helium nucleus. Second is beta decay, represented by the Greek letter beta, which involves the emission of either an electron or a positron. Third is gamma decay, represented by the Greek letter gamma, which involves the emission of a high-energy photon. Each type of decay transforms the nucleus in a different way, and understanding these differences is crucial to understanding how radioactivity works. Alpha decay is a type of radioactive decay where the nucleus emits an alpha particle. An alpha particle consists of 2 protons and 2 neutrons, which is essentially a helium-4 nucleus. When a nucleus undergoes alpha decay, it loses these 4 particles. As a result, the mass number of the nucleus decreases by 4, and the atomic number decreases by 2. The general equation for alpha decay shows that element X with mass number A and atomic number Z transforms into element Y with mass number A-4 and atomic number Z-2, plus the emitted helium nucleus. Alpha decay typically occurs in very heavy elements with large, unstable nuclei. Beta decay comes in 2 forms, beta minus and beta plus decay. In beta minus decay, a neutron inside the nucleus converts into a proton, and in the process, it emits an electron and an antineutrino. This increases the atomic number by 1 while the mass number remains unchanged. The equation shows element X transforming into element Y with 1 more proton, plus the emitted electron and antineutrino. In beta plus decay, the opposite occurs. A proton converts into a neutron, emitting a positron and a neutrino. This decreases the atomic number by 1. Beta decay occurs in nuclei that have too many neutrons or too many protons relative to their stable configuration. Gamma decay is unique among the 3 types of radioactive decay because it does not change the number of protons or neutrons in the nucleus. Instead, gamma decay occurs when a nucleus in an excited energy state releases excess energy in the form of a high-energy photon called a gamma ray. The asterisk in the equation represents the excited state of the nucleus. After emitting the gamma ray, the nucleus drops to a lower, more stable energy level. Gamma decay often follows alpha or beta decay, as the nucleus may still have excess energy even after emitting a particle. Unlike alpha and beta radiation, gamma rays are electromagnetic waves with no mass and no charge. The three types of radioactive decay have very different properties in terms of penetration, ionizing power, and speed. Alpha particles have the lowest penetration ability and can be stopped by a sheet of paper or even skin, but they have the highest ionizing power, meaning they cause the most damage to atoms they interact with. Alpha particles travel at approximately 5% of the speed of light. Beta particles have medium penetration and can pass through paper, but are stopped by aluminum foil. They have medium ionizing power and travel at about 90% the speed of light. Gamma rays have the highest penetration ability and can pass through most materials, requiring thick lead or concrete to stop them. However, they have the lowest ionizing power and travel at the speed of light since they are electromagnetic waves. The half-life of a radioactive substance is the time required for half of the radioactive nuclei in a sample to decay. This is a fundamental concept in understanding radioactive decay. Every radioactive isotope has its own characteristic half-life, which can range from fractions of a second to billions of years. The decay process follows an exponential decay law, expressed by the equation n of t equals n0 times e to the negative lambda t, where n0 is the initial number of nuclei, lambda is the decay constant, and t is time. The activity of a radioactive sample, which is the rate of decay, is measured in becquerels, abbreviated as BQ1 becquerel equals 1 decay per second. Radioactivity has numerous practical applications that benefit society. In medicine, radioactive isotopes are used for cancer treatment through radiation therapy, diagnostic imaging techniques like PET scans, and sterilization of medical equipment. In energy production, radioactivity powers nuclear reactors that generate electricity, and radioisotope thermoelectric generators provide power for spacecraft and remote installations. In scientific research, radioactivity enables carbon dating to determine the age of archaeological artifacts, tracer studies to track chemical and biological processes, and material analysis to study the composition and structure of substances. Industrial applications include quality control in manufacturing, thickness gauging in material production, and defect detection in structural components. These diverse applications demonstrate how understanding radioactivity has transformed modern science, medicine, and technology.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.